I think it's now time to move to the next presentation by Jef Huisman, and it will be about dancing with tides. Whoever knows.
Okay, perfect. Okay, many thanks to the organizers for inviting me. Yes, I will talk about dancing with the tides, and you can see the dance already. And you can also see here Mont Saint-Michel in France, one of the famous tourist places in France, where we have the strongest tidal difference, full flooding or grazing by sheep. If you look at data of phytoplankton communities, and these are data from the jetty of Nios, and they were provided to us by Katja Philippait, then what you often see is a wax and wane of different species. Here, every different species is indicated by a different color. And you see some years the blue ones are dominant, in other years the red ones are dominant, and don't go in the names, but just by looking at the picture, you see there is a tremendous change in species diversity. And the question here is, what are the underlying mechanisms? Now, very often, if you talk to ecologists, they would say, well, let's look at the climatic variation, because perhaps we had cold winters that were favorable for certain diatom types, or we had a warm spring and it was favorable for phaeocystus. And what we try to do is we try to link this this variation in species composition to environmental variation. But that's not always the underlying mechanism for species fluctuations. For instance, what we can do is we can take away the weather by isolating these communities in the laboratory and see what happens then, if they still show these species fluctuations or not. And that's actually what was done by Reinhard Heerkloos from the University of Rostock. He took a food web from the Baltic Sea. Here you see the structure of the food web with, let me see, is this a pointer? Yeah. So here we have the different phytoplankton groups. We have different zooplankton groups functioning as herbivores. There's also a top predator here, cyclopoid copperpot. So this food web here he brought into a laboratory tank, and he cultured this system in the laboratory for more than 2,000 days and counted it twice per week. So that's an impressive data set. It's also an impressive amount of work, and we were very glad that after all this work he came to us, handed this data set to us, and asked us, can you analyze it? So, well, the first thing what you do is you just make graphs, and here you immediately see right away the main conclusion. So we excluded any climatic variation. It's brought in the laboratory under constant light conditions, constant salinity, constant pH, constant temperature, and the species keep on fluctuating in abundance. So it's not caused by weather fluctuations in this particular case. They just move on fluctuating if we take the weather away. And one of the PhD students in my group at the time, she's now a postdoc, Elisa Beninka, she analyzed these data. And what she found is that these species fluctuations are actually generated by the interactions between the species. So what happens is that if a certain phytoplankton type becomes dominant, then there's always a zooplankton type that lost this phytoplankton, eats it away. And then there's room for another less edible phytoplankton species to increase. But that might trigger another zooplankton species that can graze upon that phytoplankton, graze it away, and then there's a window of opportunity for next species. So you get these changes in species composition by the community interactions, by the interactions within the food web. What she did is she did a variety of analysis, and here I show only one of her results. That is that she plotted the prediction time, so we developed a neural network model of this system, and we tried to make predictions ahead in time. So if we have a certain time point, say here at day 500, we tried to predict what happens at day 510 from our measurements at day 500. And then we can look next, how good is this prediction in comparison to the real data? Because we have the real data from day 510 in this graph. So what you can see is that the predictability is a function of the prediction time. We can make very accurate short-term predictions. We can predict quite well what happens with the plankton tomorrow, or how it will look like next week or the week thereafter. But what you also see, there's a decrease in this predictability. There's a high predictability in the short term, but there's a much lower predictability in the long term. And this is one of the signatures of chaotic dynamics. And we also did other analysis, and we could demonstrate that indeed these ups and downs of the species are a signature of chaos. There's chaotic fluctuations in this laboratory ecosystem. So we now have laboratory evidence for chaos in plankton communities, and they're generated by the interactions between the species in the food web. They also impose a time horizon on the predictability of the system. We can make very good predictions on the short term, but it's much more difficult to predict which species will dominate in 30 days from now or in 50 days from now. So there's a time horizon in this laboratory system of about 15 to 30 days. You cannot predict beyond that. Now we have done this for a laboratory setting where we excluded the climate. The next question is, what happens in real systems? What happens in natural waters? The challenge here is that we do not only have these intrinsic oscillations generated by the species interactions, but now we also have all this environmental periodicity in the system. Can be in the form of periodic variation, think of the seasons. Can be in the form of random fluctuations, think for instance of superimposed on the seasons the random temperature fluctuations. And this interplay between the biological interactions and the environmental forcing, that's responsible for the fluctuations of the natural plankton population. So how do we entangle these different components from time series? Well, what I will first do, I will focus on a system where there's very strong periodic variation. And for this I take you to the North Sea. In the North Sea we have a few so-called smart buoys, 4 in total. What these smart buoys do is they measure the total chlorophyll, so that's an estimate of the total phytoplankton biomass, every 15 to 30 minutes. And they do this since the year 2001. So for more than 10 years already we have measurements every 15 to 30 minutes of the chlorophyll and also of suspended matter, temperature and salinity. And in this presentation I will look at one of these smart buoys here at the mooring station Warp, that's close to the English coast. It's a relatively shallow system, 50 meters depth, and there's a tidal range of about 4.5 meters. And again we got the data, and one of our PhD students was so lucky to be able to analyze them, and she just arrived. She's also here in the audience. So if you have any questions you can come to me, but please also come to Anouk Blauw later on during the break. So in this system what's very important is the tidal motion, and as you all know the tidal motion is generated by the gravitational forces of the moon and the sun. So what happens is the moon the gravitation of the moon is pulling at the water masses of our planet, and to a lesser extent, because the sun is much farther away, the sun also pulls at our water masses. And if we now look at the time series of the water level at Station Warp, here you see the time series from March 2007 till July 2007, so it's for a 4-month period. You can readily identify the different periodicities in the tidal cycle. So these very fast fluctuations in water level, that's the semi-diurnal tide. So every 12 hours and 25 minutes we have a high tide, and every 12 hours and 25 minutes we have a low tide. So these are the fast fluctuations. Then you see a slower periodicity. Here we have a neap tide, a spring tide, a neap tide, a spring tide, a neap tide, and so on. And that has a periodicity of 15 days. And it's generated by the position of the sun and the moon with respect to our planet Earth. If they're all on the same axis, the sun, the moon, and our planet Earth, then we have spring tide. And if the axes are perpendicular, then we have neap tide. There's also a third cycle that you can see here. If you look carefully at the spring tides, you see here we have a high spring tide, here we have a lower spring tide, a higher spring tide, a lower spring tide, a higher spring tide, a lower spring tide. That's the Perigee Apogee cycle, and it's caused by the fact that the moon travels an elliptic orbit, and the Earth is not located in the center of this ellipse, but a bit away from the center. So the distance between the moon and the Earth varies in time. And so also the gravitational force of the moon varies in time, and that causes this Perigee apogee cycle with a periodicity of 28 days. There are also other higher order cycles. In addition to the Perigee apogee cycle, there's also perihelion and apohelion cycle of the sun, because also the Earth is not the position of the Earth around the sun is not a neat circle, but it's also an elliptic orbit, and so on and so forth. But these three are the ones that are most important for my present presentation. And if we then look at the data that we obtain from the smart buoy, then you see here in green the chlorophyll data, and you see here in red the suspended particulate matter concentration. And what you can see is that they're fluctuating up and down. They're neatly fluctuating up and down with the water level. You can see it very nicely here for the suspended particulate matter, SPM. So when the tidal range is the largest, so during spring tide, we have the highest particulate matter concentrations in the water column. And you can also see it here in the chlorophyll. So when we have spring tide, we have very high chlorophyll concentration. When we have neap tide, we have low chlorophyll concentrations. And in addition, you can also recognize that there are faster fluctuations here in both chlorophyll and suspended particulate matter. So one question here I have for you is, what will be the period of the fast plankton fluctuations? Any idea? It's trivial, right? 12 hours, right? That's what you would expect. So let's do the analysis and see whether we can find this 12 hours. And what we do is we use a technique that's called wavelet analysis. And wavelets are local waves. It's actually, it's a sine function, but the sine function is localized. It only occurs during this time frame. It doesn't occur here, it doesn't occur here. So wavelets are characterized by two things. They're characterized by their how fast they fluctuate, so by the period, or by the inverse of the period, the frequency, and they're characterized by the timing. When does this wavelet occur? Well, in this case, it occurs at this point in time. So here you see two examples of wavelet analysis for two imaginary time series. Here's one, we have two superimposed cycles. We have a slow fluctuation with a period of 5 days, and we have a rapid fluctuation with a period of 1 day. And what a wavelet analysis does is it identifies this periodicity. So here you see a wavelet plot. This is again the time on the x-axis. And red means a very significant result. So we find a very significant period of 1 day. And we find a very significant period of 5 days during the entire 60 days of the time series. Here's another example. Now I have first fast fluctuations with a period of 1 day. And then I switch to slow fluctuations with a period of 5 days. And it's also recognized, identified by the wavelet analysis. So it says first, during the first 30 days, I find a significant periodicity of 1 day, and then I switch to a significant periodicity of 5 days. That's how you should interpret these graphs. Now we use this technique to apply to our high-resolution data from the Smart Boys. And here you see the results. So in color here, the wavelet analysis. Red means highly significant. Blue means not significant at all. And you can also summarize these wavelet graphs here by this spectrum, the global wavelet spectrum. And what you can see is that there are several peaks in this wavelet spectrum. And actually, if you look at the chlorophyll data, indeed we have one peak at 12 hours. But what's very surprising is we have also a peak in the chlorophyll at 6 hours. So it does not only fluctuate at 12-hour periodicity, at the same periodicity as the semi-diurnal tide, but also twice as fast, at 6 hours and 12 minutes. There's also a third peak here. It's barely significant. It barely exceeds the dashed line, which is the red noise. It's barely significant. That's a 24-hour periodicity, which is also included there. Then if we look at the suspended particulate matter, we see a significant 6-hour and 12-hour periodicity. So the same as for chlorophyll, the 6 and the 12 hours. And for salinity and temperature, we only see a 12-hour periodicity and not a 6-hour periodicity. So that's interesting. Some of these variables show 12-hour periodicity, which is just a tidal motion. But suspended matter and chlorophyll show in addition also 6-hour periodicity. Where does it come from? Well, here are the actual data. And this is just a week of the time series. So we have 10 years of data. This is just a week. And in this particular case, February 2007. And what you can see here is the water level, high tide, low tide in blue. And then in green, the chlorophyll concentration. And indeed, you see that the chlorophyll concentration fluctuates twice as fast as the water level. Now, what we can do is we can calculate the tidal current speed from our data. And what happens is the tidal current speed fluctuates twice as fast as the water level. Because you have a high tidal current speed if you go from high tide to low tide. But you also have a high tidal current speed if you go from low tide to high tide. So the tidal current speed has a periodicity of 6 hours and 12 minutes. And if we now plot here in blue the tidal current speed with the 6 hour 12 minute periodicity, and in green the rate of change in chlorophyll concentration, you can see that these two neatly fluctuate in phase. So every time that there's a high tidal current speed, there's a lot of turbulence in the water. And what happens is that the phytoplankton is mixed upwards into the water column. And every time you have a tidal slack, so when the current speed is very low, then the phytoplankton sinks out again. So that's shown in this picture. So the diatoms sink at low turbulence and they're resuspended at high turbulence, and that creates our 6-hour, 12-minute periodicity. If we now zoom out and look at a longer time scale, I show here the daily average data, so we now look over several months of time. Then you see here the tidal range in blue, so that's our spring neap tidal cycle. And in green we see the daily average chlorophyll concentration. It's just the daily average of this more scattered line over here. It's just the same line, but now averaged out. And we can also clearly recognize the 15-day periodicity in the chlorophyll and suspended matter. That's in phase with the tidal range. And it has the same explanation. During spring tide there's much more turbulence than during neap tide. So with the spring tide you have much more upward mixing of chlorophyll and hence a higher chlorophyll concentration. And during neap tide there's low turbulence and the phytoplankton sinks again. But there's one exception, and that's the spring bloom. So that's very interesting. First we have in-phase fluctuations of suspended particulate matter and chlorophyll and spring tide. Right? They're all in phase. But then here in mid-May what you see is that the suspended particulate matter goes down, but the chlorophyll doesn't go down. Instead the chlorophyll goes up and we have a spring bloom. So here the phytoplankton escapes from the tidal mixing. What happens here actually is that we have a very strong reduction in suspended particulate matter concentration. That means that the water clears up. The water clarity becomes much higher, and in spring the water is also warmer. We have longer day periods. So this generates ideal conditions for phytoplankton growth. And the phytoplankton growth can overcome the tidal mixing. They grow faster than that they're mixed, and this generates the spring bloom in this particular system. So if I summarize these data, we have plankton that fluctuates with the tidal cycle at the 6-hour, 12-hour and 15-day periodicity. So they're all neatly in phase with the tidal cycle at these three different periodicities, but the plankton escapes from the tidal mixing during the spring bloom. Okay, the third aspect that I want to talk about is environmental noise, but I don't know whether I have sufficient time to finish it up. So I asked
4 minutes.
Can I make it a bit longer?
5 minutes.
Okay, so what is environmental noise? Well, white noise is just random variation of values. But very often environmental noise is not white noise, it's so-called red noise. And red noise is the case where we have random variation but with a memory. And I can explain this best by the temperature fluctuations. So temperature may fluctuate up and down and it might look random, but of course the temperature of today is still correlated with the temperature of yesterday, because it takes a bit of time to cool down or to heat up a lake. So there's a memory effect there. And that's red noise, and what you can do is you can draw a so-called autocorrelation function that shows the correlation, the memory effect, between the different days. So here we have the time lag, the time lag in days, and here we have how strongly the temperature is correlated between day 0 and day 5, or day 0 and day 10. And this, the rate at which this curve goes down is like a measure of the memory. The slower this curve goes down, the longer the memory of the system, so the longer the temperature stays at more or less the same value. So what you can imagine is that the characteristic time scale of red noise is very fast for a cup of coffee, because a cup of coffee cools down very rapidly. The characteristic time scale for a small lake, for the temperature fluctuation in a small lake, is about 10 days. It takes about 10 days to adjust the temperature in a lake. And the characteristic time scale of the temperature fluctuation in the Atlantic Ocean is about 80 days. It's a much larger basin, it's much deeper, so it takes much longer to cool down or to heat up the ocean. So the temperature fluctuations are slower in the Atlantic Ocean, and they're faster in small lakes, and they're even faster in your coffee if you would expose it to a random variation. Now what happens if you introduce a bit of noise in a predator-prey system? That's shown here. Here we have predator-prey model, and what you can see in this predator-prey model, at very high carrying capacity, it generates the classic predator-prey oscillations of the Lotka-Volterra model. I think you've all seen these classic examples of predator-prey oscillations. And what's interesting about noise is that if we're not yet in the phase with predator-prey oscillation, but at a slightly lower, in this case carrying capacity, where the system does not fluctuate by itself, then adding a bit of noise can trigger the system to show fluctuations. So a tiny bit of noise can amplify predator-prey oscillations. It's called noise amplification. And this noise amplification depends on the time scales. So what I've plotted here is I've plotted here the characteristic time scale of red noise. So a low value is your fast fluctuations in a cup of coffee. Very high value is the very slow temperature fluctuations in the Atlantic Ocean. And here I've plotted how strongly phytoplankton and zooplankton fluctuations are amplified by temperature fluctuations with these different characteristic time scales. And what you can see in this particular example, we find the highest noise amplification at the characteristic time scale of 10 days. And it matches the time scale of the intrinsic fluctuations. So we get maximum amplification if the time scale of your temperature fluctuations matches the time scale of the natural intrinsic species fluctuations. Now these intrinsic species fluctuations depend on the generation times of the organisms. If you have a standard predator-prey model, then you can imagine that the predator-prey model with rotifers and bacteria will fluctuate much faster than a predator-prey model with hare and lynx, or elephants and trees, right? It depends on the generation time of the organisms. So what we've done here is, for a wide range of different plankton species, we have looked at what is their generation time, or the maximum specific growth rate, and what's the time scale of red noise to which they are most sensitive, to which they show the strongest amplification of noise. And what's very interesting is that if we look at the time scales that we measure in the oceans and the lakes, that we see that cladodrons, copperpods and krill all show maximum noise amplification for these temperature fluctuations that we find in lakes and oceans. Even stronger, the oceanic groups are mostly the copperpods and the krill, and they show particularly strong resonance to the higher end of the graph, and the cladodrons are more the freshwater species, and they show more stronger resonance to the lower time scales typical of small lakes. Right, so plankton, this demonstrates that plankton communities are very sensitive to temperature fluctuations, and that these temperature fluctuations can amplify the species fluctuations in plankton communities. So to conclude, what I've shown is that in a constant environment you can find strong intrinsic species fluctuations generated by the interactions within the food web, and we even found chaotic dynamics there. And that environmental variation may entrain the community dynamics, as we have seen. The chlorophyll fluctuations in the North Sea are strongly driven by the tidal cycle. They're enslaved by the tidal cycle. But we can also have situations where environmental variation amplifies the species fluctuations, as in the red noise temperature fluctuations. So this generates very complex dynamics, and this has implications for how we do our science, how we make predictions, for instance, for multi-species communities. What I think is we should take as an example the weather forecast. First, what is very smart is they make a distinction between the weather and the climate. The climate is like the overall pattern, and what we can predict very well is the overall pattern, like at low nutrient levels, probably these and these and these species will be dominant, and at high nutrient levels we will have cyanobacteria or other groups that are more likely to be dominant. The weather is more like the day-to-day predictions. If we want to predict whether we will have an algal bloom tomorrow or next week, and there we should take into account the time scales of the different processes. We should take into account that there are important limits to our predictability. There are time horizons we cannot predict beyond 30 days whether a bloom will occur or not, just like the weather forecast cannot predict beyond a week or so whether it will be freezing or whether it will be raining in the Netherlands. And what's very important is what the meteorologists do, is they always monitor. Because if we want to make predictions for next week, we need an update of our data for next week. We always need a continuous update to make the weather forecast for the next period. And that's what we also need in ecology. We need continuous monitoring to make our predictions for the next time steps. So, how often should we monitor? Well, it depends on the timescales of your system. But for instance, I've shown for the North Sea that we can have plankton fluctuations at a periodicity of 6 hours. Right? So going out with a boat every 2 weeks is not enough, because they fluctuate at a periodicity of 6 hours. So if you have a low resolution, you're going to have a bad time in predicting the fluctuations of the phytoplankton in the North Sea. We need high monitoring frequency. And that's where I want to end my presentation. Thank you.
Thank you, Jef, for your very inspiring paper. I regret that the discussion has to be done at the coffee break.
Okay.
I feel sorry.
I will be at the coffee break as well.
I want to see you back here at 3 o'clock sharp, because 50 minutes later we have to leave this room. Yeah. Okay, thank you.